Hi everyone, welcome back to this series on cryptocurrency Bitcoin, ECDSA Math. As mentioned previously, signatures are created by a mathematical function fsig that produces a signature composed of two values, R and S. In this section we look at the function fsig in more detail. The signature algorithm first generates an imperial temporary private public key pair. This temporary key pair is used in the calculation of the R and S values after a transmission involving the signing private key and the transaction hash. The temporary key pair is based on a random number K, which is used as the temporary private key. From K we generate the corresponding temporary public key P, calculated as P equals K star G in the same way Bitcoin public keys are derived. The R value of the digital signature is then the X coordinate of the imperial public key P. From there, the algorithm calculates the S value of the signature such that S equals K minus 1 hash M plus DA star or MODP, where K is the imperial key, R is the X coordinate of the imperial public key, DA is the signing private key, M is the transaction data, P is the prime number of the elliptic curve. Verification is the inverse of the signature generation function using the RS values and the public key to calculate a value P, which is a point on the elliptic curve, the imperial public key used in the signature creation. P equals S minus 1 star hash M star G plus S minus 1 star R star QA, where R and S are the signature values, QA is Alice's public key, M is the transaction data that was signed, G is the elliptic curve generator point. If the X coordinate of the calculated if the X coordinate is the calculated point P is equal to R, then the verifier can conclude that the signature is valid. Note that in verifying the signature, the private key is neither known nor revealed. The importance of randomness in signatures. As we saw in ECDSA Math, the signature generation algorithm uses a random key K as the basis for an imperial private public key pair. The value of K is not important as long as it is random. If the same value K is used to produce two signatures on different messages transaction, then the signing private key can be calculated by anyone. Reuse of the same value for K in a signature algorithm leads to exposure of the private key. This is not just a theoretical possibility. We have seen this issue lead to exposure of private keys in a few different implementations of transaction signing algorithms in Bitcoin. People have had their funds stolen because of inadvertent reuse of a K value. The most common reason for the reuse of a K value is an improperly initialized random number generator. To avoid this vulnerability, the industry best practice is to not generate K with a random number generator seeded with entropy, but instead to use a deterministic random process seeded with the transaction data itself. This ensures that each transaction produces a different K. The industry standard algorithm for deterministic of K is defined in RFC 6979, published by the Internet Engineering Task Force. If you are implementing an algorithm to sign transactions in Bitcoin, you must use RFC 6979 or a similarly deterministic random algorithm to ensure you generate a different K for each transaction. Bitcoin addresses, balances and other abstractions. We began this chapter with the discovery that transactions look very different behind the scenes than how they are presented in wallets, blockchain explorers and other user-facing applications. Many of the simplistic and familiar concepts from earlier chapters, such as Bitcoin addresses and balances, seem to be absent from the transaction structure. We saw that transactions don't contain Bitcoin addresses first, but instead operate through scripts that lock and unlock discrete values of Bitcoin. Balances are not present anywhere in this system, and yet every wallet application predominantly displays the balance of a user's wallet. Now that we have explored what is actually included in a Bitcoin transaction, we can examine how the higher level abstractions are derived from the seemingly primitive components of the transaction. Let's look again at how Alice's transaction was presented on the popular Block Explorer figure 6.7. On the left hand side of the transaction, the Blockchain Explorer shows Alice's Bitcoin address as the sender. In fact, this information is not in the transaction itself. When the Blockchain Explorer retrieved, the transaction is also retrieved the previous transaction referenced in the input and extracted the first output from that older transaction. Within that output is a locking script that locks the UTXO to Alice's public key hash, a P2PKH script. The Blockchain Explorer extracted the public key hash and encoded it using base 58 check encoding to produce and display the Bitcoin address that represents that public key. Similarly, on the right side, the Blockchain Explorer shows two outputs. The first to Bob's Bitcoin address and the second to Alice's Bitcoin address as change. Once again, to create these Bitcoin addresses, the Blockchain Explorer extracted the locking script from each output, recognized it as a P2PKH script and extracted the public key hash from within. Finally, the Blockchain Explorer re-encoded the public key hash with the base 58 check to produce and display the Bitcoin address. If you were to click on Bob's Bitcoin address, the Bitcoin Explorer would show you the view in figure 6.8. The Blockchain Explorer displays the balance of Bob's Bitcoin address, but nowhere in the Bitcoin system is there a concept of a balance. Rather, the values displayed here are constructed by the Blockchain Explorer as follows. To construct the total received amount, the Blockchain Explorer first will decode the base 58 check encoding of the Bitcoin address to retrieve the 168-bit hash of Bob's public key that is encoded within the address. Then the Blockchain Explorer will search through the database of transactions, looking for outputs with P2PKH locking scripts that contain Bob's public key hash. By summing up the value of all the outputs, the Blockchain Explorer can produce the total value received. Constructing the current balance displayed as final balance requires a bit more work. The Blockchain Explorer keeps a separate database of the outputs that are currently unspent, the UTXO set. To maintain this database, the Blockchain Explorer must monitor the Bitcoin network, add newly created UTXO, and remove spent UTXO in real time as they appear in unconfirmed transactions. This is a complicated process that depends on keeping track of transactions as they propagate, as well as maintaining consensus within the Bitcoin network to ensure that the correct chain is followed. Sometimes the Blockchain Explorer goes out of sync and its perspective of the UTXO is incomplete or incorrect. From the UTXO set, the Blockchain Explorer sums up the value of all unspent outputs referencing Bob's public key hash and produces the final balance number shown to the user. In order to produce this one image with two balances, the Blockchain Explorer has to index and search through dozens, hundreds, or even hundreds of thousands of transactions. In summary, the information presented to users through wallet applications, blockchain explorers, and other Bitcoin user interfaces is often composed of higher level abstractions that are derived by searching many different transactions, inspecting their content, manipulating the data contained within them. By presenting this simplistic view of Bitcoin transactions that resemble bank checks from one sender to one recipient, these applications have to abstract a lot of underlying detail. They mostly focus on the common types of transactions, P2P, KH, with SIG hash, all signatures on every input. Thus, while Bitcoin applications can present more than 80% of all transactions in an easy to read manner, they are sometimes stumped by transactions that derive from the norm. Transactions that contain more complex locking scripts of different SIG hash flags or many inputs and outputs demonstrate the simplicity and weakness of these abstractions. Every day, hundreds of transactions that do not contain P2P KH outputs are confirmed on the blockchain. The Blockchain Explorers often present these with red warning messages saying they cannot decode an address. The following link contains the most recent strange transactions that were not fully decoded. https blockchain.info strange transactions. As we will see in the next chapter, these are not necessarily strange transactions. They are transactions that contain more complex locking scripts than the common P2P-KH. We will learn how to decode and understand more complex scripts and the applications they support next. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.